So let's finish our unit cell solution. Okay. So we have last time, basically we were solving a new problem around the sphere, with sphere falling down at a constant velocity in the liquid, and we placed that sphere in a unit cell with the intention of packing these unit cells together into a sphere pack. Okay. So fitting them somehow into a sphere pack. So most of the problem was very similar to solving flow around the sphere. Basically, we could use the same streamline approach. So our streamline approach was basically solving for stream function. Okay? And that stream function, so basically we can relate VR and V theta to psi. And this is for the case where there is V phi is 0 and VR, V theta are functions of R theta. So streamline approach is applicable to essentially two-dimensional problems. And we basically already, and we applied a similar, in streamline approaches, you typically, in order to solve, separation of variables is required. So psi of R theta is assumed to be function f of R g of theta. And not only that, you also have to guess g of theta typically based on the boundary conditions. So based on boundary conditions, g of theta was sine squared theta. And then essentially we got that not only that I could, let me just look up the actual solution that we got, that I now can't find. Oh, okay. So basically we had this f assumed to be a function of R, and we also looked for f in terms of like a power function, right? And we got that f of R has to be C1 1 over R, right? Or R to the minus 1 plus C2R plus C3R squared plus C4R to the 4. I hope I remember these because my notes are somewhere. Yeah. And basically, by plugging in specific boundary conditions, I will get C1, C2, C3, and C4. Okay? So C1, C2, C3, C4 were one thing in my creeping flow around the sphere. Here in unit cell approach, I had different boundary conditions, and they were in terms of A and B, A being radius of the sphere, B being radius of my unit cell. So we got a quite complex, so C1, C2, C3, C4, we get from BCs. And they essentially looked pretty bad. I'm not going to write them down now. I will actually, I don't think I posted notes. I will post that symbolic MATLAB code that actually solves for C1, C2, C3. But in symbolic MATLAB, you can actually pose algebraic equation and just say solve. Okay? And solving basically just gives you what the results are in terms of A, B, U, and whatever else you want to keep as a symbolic constant. Okay? So that's really nice. That saves a lot of work. we have learned from this homework that even when you have the actual numbers, it can be quite a lot of work to integrate. So what do I do? So basically, this gives me, we have g of theta, we have FOR, so basically we have psi of r theta. Our streamline approach gives us psi. So then to get velocity distribution, I go and plug in that psi into my VR and V theta. I have formulas for that. Okay. So then after this, VR is minus 1 over r squared sine theta, partial psi, partial theta. V theta is 1 over r sine theta, partial psi, partial r. How do I get pressure? So Stokes equation essentially gives me here for creeping flow, Stokes, or for very slow flow. So Stokes equation, I can get pressure. If I have even simpler, if I have inviscid flow, I can do Bernoulli equation. So that's beautiful that I can do that because that's the simplest one. And actually, in your homework, the computational part, you'll actually get to compare two solutions. One is the solution for around the sphere and plotted that we worked out in class. And the other one will be actually one inviscid solution that actually has things from Bernoulli. So you will see how is flow around the sphere different for viscid and inviscid fluids. Okay. Just to get a little bit insight into that. So that's, well, I guess that's now going to happen after the exam, since you successfully negotiated. All right, so Stokes gives me pressure, and then I am actually set up for calculation of force, which we know it can be lengthy. So especially in this example where I have this A, B, U, and all of these, it's actually helpful to employ MATLAB, which again you will learn how to do after the exam, to actually calculate that. And I'm not going to go through that, but basically I can also get tau r, tau r theta, and integrate over the sphere surface to actually get the force. So I will just actually give you the final solution for drag force. It is 4p mu a, which used to be my r radius u, 3 plus 2 gamma to the fifth divided by 2 minus 3 gamma plus 3 gamma to the fifth minus 2 gamma to the sixth, where gamma is my a over b. And we know that gamma cube is 1 minus porosity. So this is porosity. So let's say you trust me that this was computed correctly, which technically you shouldn't. So how will what's my common sense check that this is actually a good solution? Compared to? So as my B goes to infinity, my gamma goes to 0. Does this collapse to the Stokes formula? It does. So I will have 4 times 3 divided by 2, so I will have a 6. Okay. So that's, at least you can always do that, and you should always look for simple things like, so in limiting case, you might already have a solution from somewhere that it has been verified. Check that your limiting case makes sense. So basically, note that limit as B goes to infinity, F drag is 6P nu AU, so that checks out Stokes' formula. The only difference is that A was R and U was V infinity. Okay. Okay. Cool. This is what we actually need to now actually attempt to upscale to get the permeability of this, assuming that a sphere packing or a packing of these unit cells is actually falling down. So let's see how we are going to proceed to do that. So how do we use this? Use this to upscale and find permeability. So I evaluated the drag force on a single sphere, okay, within this unit cell. So technically, if I look at that unit cell per volume, okay, then this drag force per volume is same for the entire sphere pack as it is for the unit cell if I packed all of these unit cells together. Now, what would this drag force per volume actually be? You can see, so force per area is pressure, and then I have additional per length, right, if I have the volume. So essentially, I can evaluate this if my difference in pressure disturbance to this sphere packing falling through the thing is the only thing that I have going on. I don't have gravity effects, so I basically ignore the gravity effects here. So if I take a look at the delta pressure across the unit cell divided by the length of that unit cell, okay? And my unit cell or my sphere packing, however you want to look at it, is falling down at a constant velocity. Okay? I'm at the terminal velocity. I have force balance. So terminal velocity, this constant velocity that I fall with, is basically achieved when you have a balance in forces. You have just inertia going through. Okay? So basically you don't have any acceleration because your forces are balanced. Right? So basically my delta P over L is equivalent to this drag force divided by volume because they're balancing each other. Okay? So if I put that together, okay, so you can again look at this either as for one unit cell or multiple of them, but essentially my minus delta P over L, which is my.
Your battery is low.
Uh-oh. Does anybody have a charger for this? No? Do? Fantastic. Perfect. Thank you. Thanks for noticing. I've just go dead. All right. All right. Thank you. All right. So my delta P over L is basically difference in pressures at the ends of unit cell / sphere pack. So again, you can either look at this just within one unit cell or a packing of them falling down, however you want to look at it, is balanced by drag force per volume. Because I'm assuming that there's no acceleration. I have a constant, which is terminal velocity. Because I assume the unit cell / sphere pack falls at a constant velocity. So there's no acceleration. And in this whole process, I am ignoring gravity. So drag force is the only thing that could actually be acting. I ignore gravity. And since we solved the unit cell problem in such a way that we're actually saying, okay, for this flow disturbance, everything is happening just within that unit cell. We had a zero shear stress on the boundary B, and we also had no stuff going through that boundary. So whether I'm looking at just one unit cell or a packing of them, it doesn't matter. And my gamma, my A over B, is relating the sphere cell itself to the porosity of that sphere packing. Right? So that's why I can actually look at both of them sort of equivalently. Okay? So remember, I'm going to keep writing here. So recall the solution within unit cell assumed no interaction with other unit cells. And that was an approximation, of course. We're going to check whether that really works. So whether I look at one unit cell or multiple or more or a packing, it's all the same. So basically this then has to be, after this long story, has to be drag force divided by 4/3 B. So this is my volume of the unit cell. So I will put in what that is. 4p mu AU, and that wonderful thing depending on gamma. I'm just gonna, well, I'm gonna write it down. Okay. Divided by 4/3pb cubed. So this, and then I have here A over B cube. So A over B cube is basically gamma cube times 1 over A squared, right? So then from this force balance, I can actually figure out what is my U. So I can express U. U is equal to -1 over mu. This goes up to -3 gamma plus 3 gamma to the 6 divided by 3 times 3 plus 2 gamma cube. No, gamma to the 5 gamma cube. A squared delta P over L. Great. Now Now how do I recover permeability? I compare to Darcy's law. So I assume Darcy's law is valid and compare to the two formulas, right? And I already kind of wrote it in that way. It's delta P over L here. 1 over mu minus 1 over mu is here. What's left here depends only on the geometry of this unit cell packing. Okay? Sphere radius squared. Gamma is related to porosity, so it's a function of porosity times A squared. Okay. So comparison to Darcy's law gives me that this here is permeability. So it is a fully geometric factor. I have a function of porosity times A squared, which is grain radius, grain or sphere radius. Okay? And we will call this K unit cell for a concentrated, meaning sort of a tighter packing. Okay, we made some assumptions. We got the result what the permeability should be. The way to proceed in your research, as well as here, is to actually go and validate. And in this case, we actually need some experiments to validate, because this was semi-analytical solution. Okay, it was analytical solution, but we built in quite a number of assumptions. One of them was this idea that, oh, everything is happening within unit cell and I have no interaction with the neighbors, right? So that was an assumption as an approximation. Let's see if it works, at least to the first order, at least to some confidence. So I'm actually going to show you a graph, okay? So this here is this unit cell. I simply plugged in values of porosity. I computed gamma based on that. And I did this it's normalized per grain radius. So it's just that factor times grain radius, right? So this is actually the line, and this is a number of experiments. So this is experiments. So there was a number of experiments here on bead packs, okay? Its average actually falls right on the line, and they have certain plus minus sigma here, okay, range. So that's pretty good, okay? And then there's another sand. So these were bead packs, which were nice spheres. Sand is not necessarily spherical, so I will actually have a little bit more drag force, if you will, that we are not accounting for in this formula. And those actually fall all over here. So this is a reasonable agreement. In this is for most of the tightly packed sphere packs or sand, you will have porosity around 40%. Okay, so for randomized. So basically in this region, we're actually gonna also look at dilute. So I'm gonna write that formula down as well. So if you assume very dilute spheres, okay, then you don't necessarily need the whole unit cell approach. You can just use Stokes' formula. And if you do that, you're way off for these lower porosities. So you get a little better if your porosity is higher, right? But then if you're in this range, you're not really hitting the mark with assuming that spheres are far away, and you can use Stokes' formula. But I'm going to write that formula as well. Okay, so this is basically a pretty good agreement. So essentially, yes, we cut corners, yes, we made approximations, but we captured something essential about the geometry of this packing and the flow disturbance. So something key component is in there if you get agreement like this. Okay. So again, with the understanding that all of the formulas are approximate formulas and that you never have this perfect idealized situation that you have, this is as good of an agreement as it gets in porous media anyway. All right. Okay. So I'm just gonna write down. The other formula, so basically, technically my permeability K is not well defined as B goes to infinity because I was dividing by gamma cube and that gamma cube is a 0. But for a dilute packing of spheres, so very high porosity, spheres are very far away, so something like boop, 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 right? Then I can just say minus delta P over L is my Stokes formula. Divided by 4. So in this case, you would get, I'm just going to write the result, it's simple. 2 over mu gamma cube A square 1 over mu delta P over L. So this is called K unit cell dilute. And I have just shown you that it doesn't really work well in the range of porosities around 0.4. It actually doesn't really work well even away. I find the concentrated packing. It's an approximation. But it's a much simpler dependence. So this is 1 minus phi, right? So this is 1 minus porosity. So it's a much simpler function of porosity. Yeah.
So what is the symbol before the gamma cube? Is G or 9?
9. 2 over 9. So it took us, what, 3 weeks to derive some permeability formulas? Woohoo! This is why it's not done in petrophysics, right? So that was one way, and we're actually now going to derive another formula for permeability, just to have a range of them for the heck of it. So we are now going to move on to carbon-Kozeny. And actually, that's not going to be the last one. There will be more. For permeability.
Quick question. Why are you dividing your dress force with the unit cell volume as opposed to the drain volume? Why are you dividing your dress
Because I'm formally packing all of these unit cells. So my packing is packing of unit cells, not just volume-wise.
like what?
That's how I related gamma and porosity, if you remember.
Okay, so your drag force is the total is from all the grains in that unit cell.
Yeah. So it's basically averaged for that much volume, which has some empty space as well. Okay. Because my sphere packing has some empty space and not just grains. Okay. Okay. All right. So not all porous media can be described as packing of spherical particles. So our carbon-Kozeny model will start moving away from that model, though not completely. We will get multiple formulas, and some of them will actually work really well for sphere packs and will coincide with this unit cell approach quite well. And some of them will actually be more generalizable, so I can, just in terms of surface areas and porosity of my medium, porous medium, so I can actually start using them for sandstones or something more complicated. You have to understand that all of these permeability formulas, they will typically work well for media that basically has some sort of granularity to it, because that's kind of how things are derived, and also media that has pore sizes that is within a relatively limited single length scale range. The moment you have carbonates, shales, or anything that has a very wide pore size distribution, these things are going to start to fail. Okay? These, if you have nothing else, these are the formulas that are still used, and should I say abused, because it's better than not having anything. But they will, the moment your porous medium starts diverging from having a single length scale pore sizes, these formulas will start to fail, and then different correlations of data are basically used to correct existing data. So nevertheless, even if you're using correlations, so you know that like if you're just correlating data in general, you should have, what I say, some sort of lens through which you're looking at the data, because that gives you an idea of what the correlation should look like. For correlations to work or to find parameters or some correlation function, you need to know what that function should be. Right? And these type of analytical or semi-analytical derived formulas give you kind of the idea of what that function should be. So for instance, one thing that I don't ask you to remember the unit cell approach permeability precisely, but for both unit cell and for this carbon-Kozeny model that we will have, permeability depends on grain size square. Okay? So that is the type of dependence that actually can guide your intuition in what do you expect. So if you change your medium, how will your permeability change as a result? Okay? And then if you are looking for correlation in any other type of media, that should kind of still hold true. So that gives you a lens through how to actually formulate your correlation function. So it's some function of porosity times grain size. Okay? So when you're stretching these analytically derived formulas to some media that they were not derived for, they're still useful to guide you in that process. Okay, so so Carmen worked on this, by the way. Carmen worked on this in 37 and 38. 20th century, of course, and Kozeny worked in 1927. Let me write that down so there is no confusion. And the approach that I'm going to describe here is a combination of their works, and it's also, for reference, you can go to Larry Lake. Enhanced Oil Recovery book, and there is a chapter 3 on petrophysics. So if you need a reference, that's where you can find it. Okay? So main idea in this approach is that a porous medium, it seems that that's the only thing that I will have the time to write. Main idea: a porous medium is assumed to be equivalent to a channel with an irregular cross section but that cross section on average has constant area. So the whole point in upscaling this will be finding, well, what is that equivalent channel that actually describes flow through my porous media. This was actually borrowed from so-called hydraulic radius approach. So my hydraulic radius, RH, is basically this cross-sectional area open to flow divided by a wetted perimeter. So that's for that channel of constant cross-section, and if I basically now multiply that to get a volume, I'm going to get void volume of porous medium divided by surface area of these channels within the medium, right? Of pore space within. So we will continue with this approach on Monday. So again, this is basically 2 here, midterm. Okay. All right. Okay. So I will post complete set of notes and also an example exam